data. Okay, so I can start. I'm ready to go.
Yeah.
So hello, everybody. Thanks for this invitation. So it's I taught a lot this way, but giving talks is didn't do so many times. So let's see how it goes. So I will report about recent work I did with Felipe Kucker and Pierre Leray. I think very exciting research. My talk will be very untechnical, so don't worry. It will be just an overview talk. So, okay, next slide. Okay, okay. So it's about solving polynomial systems, very general problem. I'm given n homogeneous polynomial equations of degree d in n+1 variables. I'm looking for a solution in complex projective space. And we always know there is a solution, and the problem is how to find one or how to compute one approximately. So this question, of course, has been studied for many, many decades, and it's impossible for me to summarize everything what has been done. So just very brief overview. So think of the situation where these polynomials are sufficiently generic. Then we know by Bézout's theorem that the number of solutions is d to the n. Okay, so we know that. And there are algebraic algorithms known that compute all d to the n solutions very fast, namely with a number of operations d to the on. So it's about, it's polynomial in the number of solutions, like work by Reniger and many other people, Giusti, Le Cerf, Salvi, etc., etc. And the question was for a long time whether we can, what happens if we just want to compute one solution or a few, not all of them, okay? Can we do significantly better than this d to the n, okay? And it turns out that if you switch from algebraic algorithms to numerical algorithms to numerical homotopy continuation algorithms, you can do much, much more. Okay, you can actually achieve this. Okay, so homotopy continuation algorithms, they have been known for quite some time, I think since the 30s of the last century, and they are very much used in practice. But the complexity of such continuation algorithms has been investigated, I think, systematically for the first time in a series of work by Schub and Smale in the 90s. They wrote 5 papers calling Bézout, complexity of Bézout theorem 1, 2, 3, 4, 5. Very interesting investigations, very seminal papers. And at the end of this series, there was a problem posed by Steve Smale. It's nowadays called Smale 17th problem. And it was the following. So let me read it to you. So can a zero of n complex polynomial equations in n unknowns be found approximately on the average in polynomial time with a uniform algorithm? So, okay, of course, there are several notions here that are not rigorously defined. So let me explain a little bit what I mean. But before doing so, I can tell you this question actually was solved. There is a positive answer. And the solution is, in the end, it was due to Pierre Leray, based on work by Schub, Smale, Beltran, and Pardo, and myself with Felipe Kucker. So what is the meaning of these statements? So the assumption was that these polynomials are given in dense representation. So you have these polynomials given by the list of their coefficients. So the input size would be the number of coefficients, and is this capital N, which is this binomial coefficient, number of monomials times n. Okay, and what does average mean? I mean, there is a notion of an approximate root. Maybe let me not go into details here. It also has a precise meaning. Polynomial time, I mean, I think you will understand the running time should be polynomial in this capital N. But what does it mean on the average? So it was assumed that these polynomials, these inputs, they come with a distribution. Okay, and there is a very natural distribution to use here. The distribution is invariant under unitary transformation, and it's not unique, but in a way almost unique. So it's a very natural question, and this sometimes it's called the Kostland distribution, Bombieri, or Weil distribution. So this was the assumption. Okay. But the question that I want to raise now is, how meaningful is the dense model at all? So there have been, there have been some more after Leré's paper. Well, after these papers I mentioned, there has been some improvement, and actually Pierre Léré, again Léré, 3 years later, came with a significant improvement, different framework, and he proved a running time which is essentially quasi-linear. So the cost is some polynomial in n and t times capital N. So it's almost linear in this capital N, which you think of is a big number. So in a way, it's essentially optimal for the dense model, which is very nice result. But the problem is there is a huge gap between this theory and practice. So there is a lot of implementation done, practical work, even in engineering, very successful. But somehow this theoretical result cannot explain this, because the systems of interest, they are always structured in some sense. So you think of these structured inputs, somehow they lie in a set of measure 0 in the input space of all polynomials. Okay, so this, because they lie in a set of measure 0, this result by Léré, and I mean, the solution to Smale 17's problem doesn't tell us anything about this behavior of the above algorithms on these structured inputs. So we don't know. Okay. So in that sense, one can say that the dense setting is only the first step towards understanding the problem. Okay, and the goal of my talk and the results I'm going to present is to go a step in that direction. Okay. Oh, I see. Maybe I'm not even in the most recent slide, but it's okay. Right. There's a problem here. It seems that I'm in the wrong slide. Okay. Okay, can you hear me?
Yes.
Yeah.
Okay, sorry about this interruption. So actually what we ask about the refinement of Smale's question for structured systems. Okay, I think Smale's question for structured systems. It's not completely rigorously defined, because the question is, what does structured mean? Okay, there are many ways to interpret it, but before I'm telling you our choice, let me explain to you some really important feature that we wanted to retain. And this is the unitary invariance. So for all the results I've mentioned so far, unitary invariance is an important feature, very important. So what do I mean by this? Okay. So we have this unitary group, un plus 1. Yeah, everybody knows what it is. It's something like, orthogonal transformations. And these unitary groups acts on our space H of homogeneous polynomials of degree d in n plus 1 variables. And what is the action? Just coordinate transformation. Okay, you should think of orthogonal coordinate transformation with somehow geometrical meaningful. But right, our inputs now consists of n such polynomials. So we are allowed to transform each of these polynomials independently. So the group which is acting here is actually a product of n unitary groups. So I denote this product with the calligraphic U, okay, acting on this space with the calligraphic H, n tuples of homogeneous polynomials, and this is just the action. It's composition, it's precomposition, okay? And the new result I'm going to explain to you applies to structure settings that respect the unitary invariance. We really wanted to retain this unitary invariance. Otherwise, I mean, the analysis is terribly difficult, okay? And what we actually will do, I will tell you about an algorithm and an expected running time. And the running time will be over an orbit. So you have an input system, f1 up to fn. You act with this group, so you get an orbit, and you will average the running time over this orbit. So this will be the nature of the result, an average over the orbit. Okay, right. So now, what does structured mean? There are, of course, many, many ways to do this. I think that one of the most natural things is the following: sparse systems. So you would prescribe the support of the polynomial. So support meaning that you you prescribe which monomials to occur. Let's say only few monomials. So this is very natural. And there is substantial work by Gregorio Malachowicz in this setting, even though he didn't manage to, I mean, he designed algorithms and analyzed them, but he couldn't do a probabilistic analysis so far. And one of the problems with the sparse model is it's not unitary invariant. That's pretty clear. Say you have very few coefficients, you make a transformation, you lose the whole structure. Okay. So for our results, we don't focus on sparse, it's different. Actually, we assume very, very little about these polynomials. The only thing we assume is that the polynomials are given by a black box. So a black box is some evaluation routine that can evaluate. So you give x and the routine spits out f of x. And you don't even know what the routine does. That's why it's called black box. Otherwise, it would be called white box. You don't look into it. It's just this evaluation. Okay, very, very little information. And actually, this assumption is quite common in optimization. As you probably may know, in optimization, often people just assume the function and maybe its gradient are given by a black box and not more. Okay, so we assume this here as well. We don't even assume direct information on the gradient. Maybe something to observe here is that this is really, this black box model is compatible with this unitary invariance, because if I have a black box for fi here, and then I transform my fi with my unitary transformation, well, for the resulting polynomial, it's very easy to get a black box. You just, first apply ui and then the routine for f. So I stay in this framework. Okay. So now I move quickly to the statement without. So now I tell you, I will state the main result. So, okay. So the input is a system, capital F, consists of f1 up to fn, such homogeneous polynomials. And I will assume that the zero set of all of these polynomials has no singularities. So it's somehow non-degenerate. And then what we do, we assign to this system some quantity reflecting a numerical conditioning. So I'm not going to give the definition here right now. If you ask me, I can explain later on. So what we actually have is, okay, to each fi, okay, we assign some number, gamma of fi, and then we combine all these numbers in one number capital of the system. So here it's like an L2 combination, but it could also be a maximum. It doesn't really matter. So this is this numerical quantity tells us somehow how good is fi numerically. And for those who have looked into this a little bit, let me tell you what is this gamma fi. So maybe you know this small gamma quantity, which is assigned to a system and a solution. So here analogously, you can assign it to a system and one z. And what we do actually, we average this quantity over the zero set of fi. Okay, so this is the nature of this thing without details. So you have this numerical quantity gamma, and there is another quantity which I denote L of f, which is the number of arithmetic operations that are sufficient to evaluate f. So this is like the straight line complexity. Okay, so we have two parameters which belong to f, and here is the first, okay, result. So we exhibit an algorithm. BBS stands for black box solving. What does it do? So the input is a system, capital F, as I told you, given as a black box, and some tolerance epsilon, positive epsilon. And the algorithm computes an approximate zero of the system with probability at least 1 minus epsilon. So it's a Monte Carlo thing. It may fail, but the probability of failure is at most epsilon. And here we have, okay, we can say something about the running time. Here is the statement about the running time. So as I said, the running time of this algorithm tells us about, well, is about the average running time taken over the orbit. So you have your system F, you apply a random unitary transformation. I write it U dot F, it's just this transformation. And on that input, okay, when U is random, the expected running time is at most that. You have some polynomial in N and D times straight line complexity times gamma F log gamma F plus log 1 over epsilon. So I think it's an excellent upper bound. It's certainly polynomial in all the parameters, okay? The dependence on epsilon is almost neglectable. It's the log 1 over epsilon, okay? So I think that's one result. Okay, what can we do with it? So this was an average over an orbit, but you can apply it to any distribution of input polynomials that is unitary invariant, okay? And then you get, this is almost immediate, but just let me restate it. So if I have now a distribution somehow, unitary invariant, then on a random input, our algorithm, black box solving, has an expected running time bounded by this quantity. This should be, sorry, this is a typo. It should be the polynomial in number of variables, degree L. L is an upper bound on the LF. And the gamma here is an average of the gamma F. Okay, mean square average over the input. Okay, so what we did now, the question was, okay, we have this general result, but the question is, in order to really understand how good is this, maybe we would like to know for, in specific situations, what is this gamma? If it can be very, very big, we wouldn't be very happy. So somehow we want to show in interesting examples that this average condition measure gamma is small, okay? And actually we managed to do this. That was quite technical. So we were looking for a class of structured system where we actually can bound this. And then we came up with this very well-known model of algebraic branching programs. It's a very well-known model in algebraic complexity theory, and I will explain it to you what this means. So anyway, this model is unitary invariant, and by definition in this model, the systems have small complexity. And we have a natural invariant Gaussian distribution in this class. And actually, we managed to effectively bound this gamma in that. Actually, this should be not gamma F, it should be gamma. This is a typo. Okay. So now I will, now I'll explain you what are these branching programs. Okay, it's also untechnical. So the algebraic branching program, so just briefly ABP. They were introduced by Noam Nissan long time ago in 91, and they are quite important in algebraic complexity theory. So they appear in this valiant theory, VP versus VNP. They prominently appear there. And actually, the definition of algebraic branching programs is very combinatorial. So I was tempted, because this is a combinatorics seminar, I was attempted to give the the graph theoretical definition, but I realized half an hour is very little time. So I will not do it, but you are invited to look at it for yourself. The most concise way to define the model is using matrices, which I'm going to do now because it's short. So what we have some parameters, format parameters, R0, R1, RD, they describe the format of matrices. And what I take D matrices, so A1, A2, it's up, etc., up to AD. And each matrix AI has as entries linear forms in variables Z0 up to Zn. Or you may also see it this way. I have this matrix here, AIZ. I can also view this matrix as a linear form in the variable Z, where the coefficients itself are matrices. So, I mean, there are two ways to see it. It's all the same. Now this matrix has a format Ri minus 1 times Ri. So it's just made in a way I can multiply together all these matrices. So I can multiply together. This makes sense because, right. So because R0 equals Rd in the end, I get a square matrix and I can take the trace. Okay, I get this polynomial F. So this is just called, this is iterated matrix multiplication. Okay, and this polynomial F is what is defined by the branching program, or people say this is the polynomial computed by the branching program. Okay, right. And I mean, if you would just write out the definition of F, you will get a huge sum, the exponential sum. If you just stare at this sum, maybe it's not clear that you can efficiently evaluate, but if you look at the structure, you see, well, you use that matrix multiplication is associative, and then using that, it's very easy to see that you can evaluate this with very little arithmetic operations, n, d, r to the 3. So the r to the 3 is for multiplying two matrices, you know, not the fastest way, but just the silly way. Then you have d matrix multiplications. And each evaluation of an entry of a linear form costs the operation. So you get this n d r cubed, easy. R is the maximum of the Ri. They are sometimes called width. Okay. So, by the way, I mean, I don't have much time, but maybe I may mention that this model here of this matrices, where the entries are linear forms, is also recently played a prominent role in connection with factorization. So there is this famous question going back to Edmonds. You have a square matrix, and the entries are these linear forms. And then you look at the determinant, and you want to know whether the determinant of this matrix vanishes identically. How can you do that? Well, if you have randomization, it's very easy. You just plug in values for the variables and to check it. But the question is, can you do without randomization? This is a very important and open problem in computer science. It's somehow related to that. Okay, that was a side comment. Okay, this is branching programs, and then we need the randomization. Okay, so we came up with this concept of Gaussian algebraic branching programs. It's very natural. We just assume that our matrices Aij are independent, complex standard Gaussian matrices. Okay, so then now because the Aij are now random, our polynomial f will be random. So we have this random polynomial f, and it's highly structured. Okay, it's not so easy to understand. It's a highly structured thing. But easy to see by construction, the distribution of this random polynomial f is unitary invariant. And the support, now this is actually what we wanted. I mean, the support of the distribution, the set where it lives, is low dimensional. So you should imagine you have this enormous space of homogeneous polynomials of degree d in n+1 variables, and in that a very thin algebraic subvariety where these special guys live. So the dimension is very small. Okay. Right. And so here is the second theorem. Okay. So we want to, okay, we apply the first theorem to this setting. And then the question is, what is this average gamma square? Okay. And then we proved this bound. As you can see, the expectation of the gamma f squared is bounded by something very, very small. 3/4 d cubed times d plus n times log d. So this is a very small bound. Okay, provided, okay, there is a technical catch, very harmless. All these matrix formants here are at least 2. Otherwise, you get infinity almost surely. Okay, gamma f is almost surely. So, okay, this proof is no time. Don't worry, I will not enter it. It's quite, I would say it's a technical tour de force. It was hard to get this. But you see a corollary now, combining what we have, we get the following result. We can now efficiently solve systems given by Gaussian algebraic branching programs. So here is the corollary. I have a system f1 up to fn given by independent Gaussian random algebraic branching programs of degree at most d of these formats R. and evaluation complexity of most L. Then this algorithm, black box solving, computes an approximate zero of the system with probability at least 1 over epsilon, okay, with that many operations on average. You see this bound is very little, some polynomial nd times L times log 1 over epsilon. So I mean, it's certainly polynomial time. So I see this result. Okay, let me see if I can go on somehow as a first step towards providing an affirmative answer to a refined version of Smale's 17th question. So concerned with structured system of polynomial equations. Okay, so I have 2 more slides now. I don't know how much more time I have. I have 2 more slides to explain a little bit what is behind, which I will try to do now.
Yeah, you can have 3 more minutes because
3. Okay, good. 3. Okay, then okay. Okay. I mean, what I have. Okay, there was nothing technical. I mean, if I want to explain what's going on, I would need to explain first the framework of rigid homotopy. There's not much time, but let me throw at you some keywords at least. So there is a general framework due to Pierre Leray, which substantially improves the Schub-Smale framework. And this is the basis of our work. So the paper was published last year in JAMS. Okay, so what is it? Okay, how can I summarize in very, very short terms? Okay, assume we are given such a system, capital F, okay, as before. Then we assign to this system, capital F, something that we call a solution variety. So what is that? So this solution variety consists of pairs. On the one hand, you have an element of our group, so U1 up to UN, these transformations, unitary groups, times a zero of the transformed system. So your given system is transformed with the U's, and then Z should be a 0. So this is what we call solution variety. The solution variety has a natural action of the unitary group, and we have it's compact, the thing is compact. So we have a unitary invariant probability distribution. And the one key point is that, in fact, it's possible to sample in this variety. So there's a way to efficiently compute a sample according to this distribution, which I don't have time to explain. It's not very hard to explain, but you can sample. Okay, and these samples somehow serve as a starting point of homotopy. So the framework of homotopy continuation is a very general framework, has been known for a long time, but this is now applied here. So what you have, now we have sampled the point UZ. Now you connect your U to the identity. You have the identity in the group, you connect it by a geodesic, think of some rotation. You connect it by a geodesic path. T goes from UT, okay? And then you lift this, okay? You want to lift this, and almost surely the lifting is possible. So actually you contain the 0Z by a path, which now is in the projective space. So that's the idea. This is a very general idea, and okay, I don't have a picture to explain it. You may ask if you want to know more. This is a general principle. And what's new about this algorithm then? Okay, this was a very general mathematical idea, but if you want to implement it numerically, you have to define step sizes. So usually the simplest way to do this is to discretize, and you have Newton steps, but you need to know the step size. So Smale and Schub, they had analyzed this already, and step sizes are determined by Smale's parameter gamma. Okay. So actually, previous work, the work by Schub and Smale, in the end, what they did, they estimated the gamma by the condition number, because the condition number is easier to deal with, but this leads to large step sizes and is too wasteful. So you cannot get the results as good as we get with that. We really have to stick with the gamma. That's very important. But the gamma, what is the gamma? So, okay, very tiny writing. The definition of gamma is written here. but it's important that it involves the norm of the higher order derivatives. So this is something maybe not so easy to put your hand at, okay? So here, what do we have here? Like the kth order derivative of f at z, some norm. But this thing, now here is an idea. What you can do, you have your polynomial f, you shift it by z, you shift it. And then you, from the resulting inhomogeneous polynomial, you take the homogeneous part of degree k. And actually, the norm of this, if you take the right norm, okay, then you have to look at the while norm, essentially an L2 norm of this thing. Okay, so the point here for this algorithm is that there are some tricks from algebraic complexity. The trick is that this p, so the shift, the homogeneous component of degree k of the shifty polynomial is easy to compute in the black box model because the shifting is easy, costs nothing, and taking the homogeneous part is some interpolation trick. So this, you stay in the model. And then one algorithmic idea was to estimate this gamma using Monte Carlo, because one can write the while norm. You think of this polynomial, the while norm, you can think of the average. It turns out this is up to a constant. This is the squared average of the function. You take p absolute value squared, you average over a sphere or a ball, it doesn't matter. It gives you this. So actually what we do a sampling. So we do a sampling. That's how we do the step size. So the point is, actually in our algorithm, it's a bit crazy. So before we do, when we do the homotopy, how do we get the step size? Very theoretical. We do a Monte Carlo sampling to find the step size. So that's why the whole algorithm is a Monte Carlo thing. And then you have to analyze very carefully, okay, to come up with your results. Okay, I think that's what I wanted to say. Thank you for your attention.
Thank you very much.